copy. Thank you, Jennifer. Anyone else in the room need a copy of the chapter 6 notes? Because I still have quite a few left. I think someone else needs to look up. All right. Well, let's start by reviewing. When you solve a logarithm, what are you solving for? Yeah, for the exponent. So this is kind of interesting because, you know, we've been talking about what it means to solve for x, like for anything. What does it mean to solve for x? So if I were to write down just any equation, like x squared plus 7x plus 12. If I said solve for x in this scenario, solving for x, you know, you would just factor it. And then you'd use the zero product rule and say that x is -3 and -4. Well, at that point, you're not done solving for x yet. You've just done a little bit of algebra, and it led you to two possible numbers. Now, to actually solve for x, you have to take those numbers and plug it back in and show that it makes it true. So if I plug -3 in here, I would get the sentence 0 equals 0. So that's certainly true. And if I plug -4 into this sentence, I would get 0 equals 0, and that's certainly true. So this is really the end of the problem when you solve for x, is you get down to some sort of true statement. So now when we're talking about logarithms, like when I say 5 to the power of what is equal to 13, now logarithm is just a very specific case of solving for x. Not only are you solving x, just like you've always been solving for x, it just so happens that x happens to be in the exponent. So a logarithm is solving for x, just like we've always been solving for x. It's just that now instead of the x being the base, like in a polynomial, now x is in the exponent. And so that's the special word logarithm. How do you read log base 2 of 16? Other than what I just said. That's technically how you'd read it, log base 2 of 16. What does it mean? Yeah, 2 to the power of what equals 16? And I just want to reiterate, when you look at that and you say, okay, 2 to the power of what is 16? You might say, well, why do we even have this notation? If that means 2 to the power of what is 16, that's literally writing 2 to the power of what is 16. Right? That's the same. Saying 2 to the power of what is 16 is literally that equation right there, 2 to the power of what is 16. And what I want you to notice is that in mathematics, and in fact, I might even just show a fun quick proof. In mathematics, you're always allowed to do something. This is really fun and clever. You're always allowed to take an expression and look at it and say, I have no idea what that is. I don't know what that is, so I'm just going to go ahead and say, let it equal x. It's a very clever start to how to solve a problem in mathematics, is take something that you're not sure what it is and say, well, let it equal x. Because then from there, you can use definitions to rearrange this and put it in a form that you know. So for instance, what we were learning the other day is it's left to the right equals middle. That if you have a logarithmic expression, you go left to the right equals middle, and you get 2 to the x equals 16, which is the same as just knowing how to read the logarithm in the first place. Okay, so that's that. Convert 3 to the x equals 81 into log form. So how would you write this as a logarithm?
Log 3, 81 equals x.
Yeah, very good. Log base 3 of 81 equals x. Okay, perfect. That's it. That's converting an exponential expression back into log form. And folks, you'll notice the first number, the base, stays the first number. So we went from 3 to the x equals 81, and it turned into log base 3. So the first number stays the first number. It's just the second two numbers that switch sides. So now I have log base 3 of 81 equals x, and the x and the 81 switched. All right, convert log base 5 of 125 equals x into an exponential form. Well, gee, we already did something like that. Again, it'd be left to the right equals middle, so 5 into x equals 125. And then what base is log? If you just look on your calculator and you see the log button itself, what base is that? That's base 10. And if you look at the button on your calculator, ln, what base is that? E. So you only have 2 log buttons on your calculator, except for Emily. She has other log buttons on her calculator. Does anyone else have a calculator that allows you to change the base of the log? You do, Val? You do, Evan? Yeah. Okay, so a few of us do. I've never myself personally owned a calculator that allows you to change the base. That's a pretty fancy technology. We're going to learn how to change the base on our calculator, even if you don't have that type of calculator. It's just an extra step. All right, so did anyone go home and have any dreams about logarithms, or, you know, sat up late at night and read about it on Wikipedia and you have some questions? You're like, hey, Mr. G, I was wondering about this logarithm stuff. Anybody? No? Okay. Well, then let's keep going. Today is, what, October 24th? So we're continuing on our way. You know, when I put these numbers in here, 61, 62, 63, 64, 65, these are all pretty flexible. And I built in the review day to give us more time. So I think so far we finished 6-1. So today we're starting in the 6-2, and we'll just continue moving on through the chapters. And I will probably have to change this due date a little bit, because the only chapters that we'll be doing more after today will be whatever we finished on Monday and Wednesday. So just know that I'll probably have to update that. Okay, and let's see. I already did the what did 0 say to 8. Then what does a... Did I do this one? What does a nosy pepper do? This is a funny joke. You're all going to want to tell this joke to your friends. What does a nosy pepper do? It gets jalapeno face. Yeah, that's a good one. All right. That was probably the most giggles I've heard all semester. See, that was really good job. All right. So at the end of last class, we had just started talking about this notion of log properties. And log properties were a few special rules. I'm going to write them down again. You have the product rule, which states that the log of a product of two numbers, log of AB, is equal to the log of A plus the log of B. So that's our first rule. One way that might become obvious to you is if you were to try out a simple example like log of 10 times 10. So log of 10 times 10 is really log of 100. And so now let's all calculate this. What 10 to the what is 100? 10 to the power of what is 100? Because this is base 10. Remember, if I just write log, it's base 10. So 10 to the power of what is 100? 2. Now let's come over here and use the equation. Log of 10 times 10 is really log 10 plus log 10. Because I can split that up over the product. So now 10 to the what is 10? Just 1, and that's also 1. And therefore, 2 equals 2. So the formula does work. And that's called the product rule. Likewise, you have a quotient rule, which states that if you have the log of a fraction, log of A over B, then you're allowed to split that up over subtraction. So log of A minus log of B. And again, we could do a simple example of that. We could maybe do log of 100 over 10. I'm choosing 110 to keep it simple so that these are examples we can do in our head. If I have log of 100 over 10, that's really log of 100 minus log of 10. And you might want to keep in mind, it's top over bottom, top minus bottom. That helps you remember the order of things. Log of top over bottom equals log of top minus log of bottom. Okay, so then 100 over 10 is just log of 10, which 10 to the what is 10? 1. And then over here we have log of 100, 10 to the what is 100? 2. Minus log of 10, which is 10 to the what is 10? 1. And 2 minus 1 is 1. So again, I don't know if you wanted to be convinced that the formula works, but these two formulas work in at least these two simple examples that I gave you, and I'm guaranteeing you they always work. All right, and then finally you have the last rule, which is the power rule, which states that if you have, say, log of A to the power of n, where n is any exponent at all, it doesn't have to be a whole number, it could be negative, it could be a fraction, it could be anything at all, then that's equal to n times log of A, which means you get to bring that exponent out in front. So again, as a simple example, let's just say we had log of 10 squared. That's really log of 100, which we all know 10 to the what is 100 is 2. And then over here, I get to bring that 2 out front, so that's 2 times log 10. And then log 10, that's 10 to the what is 10, that's 1, so that's 2 times 1, which is 2. All right, well, there we have it. These are our 3 rules that we're allowed to use when manipulating logarithmic expressions. Now you might say, Mr. G, why on earth do we want to manipulate logarithmic expressions? That's a good question. I think the idea is just to be able to simplify expressions. Like this looks pretty complex and nasty, whereas if we were able to split that apart into simpler terms, that would maybe be easier to type in your calculator, or maybe easy enough that you could do each part in your head. It's just a matter of simplifying. I mean, why do we simplify anything? Why would we simplify the fraction 216 over 36? Like, you just look at that and you think, well, that's a pretty nasty looking fraction. But then you type it into your calculator and realize it's just 6. Well, of course, there's very good reason to simplify fractions so that you're not dealing with big numbers unnecessarily. So yeah, we want to learn how to use these rules in order to rewrite expressions, because sometimes it's helpful to rewrite expressions. I feel like there's something else I wanted to tell you about that. Well, it'll come. So, did we already do the first one? Yeah. I think we did. So let's try the second one. We have log base 5 of z over 25 all to the power of 3. So which rule applies? That's always the question you want to ask yourself. What rule applies? Or rules, I should say. Does the product rule apply? Do I have something times something? No. Does the quotient rule apply? Yeah, we have a quotient. Does the power rule apply? Yeah. So we have both rules. We have the quotient rule and we have the power rule. So in what order should we do it?
Quotient first.
Yeah, see, now this is a tough one. If we did, the quotient is being wrapped up inside of this cube power here. So we technically have to do the cube power first. You might think of it in terms of solving for x, right? If you were to solve for x, like let's just say that I had x over 25 cubed equals, I don't know, some number, I'll just say 7. Then what would you have to do first to solve for x? Multiply off the 25 or cube root it? You'd have to cube root first. So when you're dealing with an expression, you want to think about outside in, just like you'd be solving for x. So the first thing we want to do is the power rule. So if you have, I'm just going to rewrite it, log base 5 of z 25ths cubed, we can go ahead and do the power rule, which states you can just bring that 3 out front. So everybody go ahead, bring that 3 out front, and now we just have 3 log z 25ths. So I think already you would say, hey, that's better. I'd rather multiply something by 3 than cube it, wouldn't you? Like if you had to do this all in your head, wouldn't you always rather multiply something by 3 instead of multiplying something times itself 3 times? Just imagine a simple example. Would you rather take x plus y and cube it? Or would you rather take x plus y and multiply it by 3? I mean, this one's pretty easy. You distribute the 3 and you get 3x plus 3y. Cubing it, you'd have to multiply x times y plus x times y plus x times y. And you'd have to do FOIL twice. You'd have to FOIL this. And then whatever happens there, then you'd have to distribute the x and everything. Oh, it's a mess. Nobody wants to cube something when you can just multiply by 3. Okay, so now what do? Now what rule applies? The quotient rule. So now watch closely. We're going to write 3 and then a big bracket. Because we want to make sure that 3 gets multiplied by this whole thing, whatever it is. And so we put the brackets there to make sure that we just rewrite this expression. So how do we rewrite log of z over 25?
Log z.
Yeah, log z
minus
log 25. There we go. So far, so good. We've applied 2 rules so far. We applied the power rule to bump that exponent 3 out in front, so we're just multiplying. And now we've applied the quotient rule so that we really have a subtraction of 2 logs. And what's one more thing that we can do? Then we can all simplify this. Log base 5 of 25. 5 to the what is 25? 2. So now we have 3 outside of log base 5 of z minus 2. And at this point, we can be done. What we've done now is we've expanded this logarithm as much as possible. We would say that we have expanded this logarithm as much as possible. Because instead of taking the log of something that's being divided and cubed, now at most, we're only ever taking the log of a single expression. And that's what we mean by expanding a logarithm. That every log now takes a single simple input. Here, this log was getting a very complex input that we had to first divide it and cube and then put it into the log. Now, the only logarithm that we have is a single input. And so theoretically, that's going to be easier for us to do. I suppose if we really wanted to, we could distribute the 3 now and call this 3 log base 5 of z minus 6. And perhaps that would be the nicest looking answer because then you don't even have any parentheses. Now you tell me which one looks better. I mean, hopefully you think the one on the right looks better. I'm not sure if if you're really convinced, because let's count the computations. We plug the z in a log, we multiply by 3, we subtract 6, that's 3 computations. Here we take z, we divide it by 25, we cube it, and then we plug it into the log. There's 3 computations either way, so you might argue that both of them are equally simple because they require the same number of computations. That's just the base.
Okay.
That's the base of this particular logarithm. All right, folks, let's try again. Take a look at this one. Now, first of all, what base is this log? This is log base e. And whether you do this whole problem writing ln, or if you want to change it and write log base e, that doesn't matter. You can do the whole problem writing log base e over and over again, or you can do the whole problem just writing ln. But the rules that we're looking at are going to work the same way. So what do we have here? Do we have a product rule? We do have a product in the denominator. Do we have a quotient rule? We do have a quotient. And then finally, do we have a power rule? This one's a little more subtle. Do we have something being raised to an exponent? Well, that's true. You've got the exponents of 1, right? We'll ignore those because everything has an exponent of 1. But that's a really fine point there, Annabelle. What's the square root of z? How do you rewrite the square root of z? It's z to the 1/2. So yes, indeed, we do technically have a natural log of z to the 1/2 over xy. And the whole thing is a quotient. So we have a product, a quotient, and an exponent. Okay. What do we do first? We need to do all 3 rules. I would suggest to you, well, I know for sure the answer is that we have to do the quotient rule first. I'm trying to think of what's the best way to explain why we have to do the quotient rule. Let's just say that you had z to the 1/2 over xy equal to some number like 7. What's the first thing that you'd want to do? You would multiply the xy over the other side so you don't have fractions anymore. In fact, some of the problems we were just doing, the first thing we wanted to do is cancel all the denominators. That's what we were doing with rational expressions. Cancel the denominators, get rid of the denominators. Gosh, it's so similar in so many ways. If you have an equation, it's like square root of x plus 3 equals 8. What's the first thing you want to do? Cancel the square root. If you have an expression that has a fraction, what's the first thing you want to do? Cancel the denominator, right? So we mathematicians, we're always trying to make things easier on ourselves. We're always trying to get rid of that which is complicated. So we want to get rid of the xy, which means get rid of the fraction. So we're going to apply the quotient rule first. So now we have top over bottom. We have natural log of the top minus natural log of the bottom. And we're still thinking about it in terms of how you would solve an equation. First thing to do is get rid of the denominator. So first thing we're going to tackle is the fraction, which is the quotient rule. And then what? We only have 2 rules left, the product rule and we have the power rule. Yeah, we can go and do the power rule. That 1/2 can just come out front. So then we'd have 1/2 natural log of z. And then now we're about to do this product rule. Again, it's very important that we go ahead and set up some brackets. Because we're subtracting something, we want to make sure that whatever we turn the natural log of xy into, that the whole thing continues to be subtracted. Gosh, couldn't there just be a whole class on the use of parentheses? Wouldn't that be wild? You're like, Gateway, Math 172, the proper use of parentheses in all contexts. Wow, that sounds like an exciting course. Okay, so then how do we rewrite natural log of xy? It's just a simple product. So you'd write it as natural log x plus natural log y. And I'm going to make myself some room here. So my final, getting rid of the brackets, would be 1/2 natural log z minus natural log x minus natural log y. Because I just distributed that minus sign. And there we have it. Again, we call this log expanded. It's expanded because now every logarithm takes a single simple input. And in certain contexts, that's helpful. If you're only ever inputting a single thing into the log, as opposed to here, you have this massive expression that you are inputting into the log. So that's one way in which we say we simplify a log, is changing a complex input into a bunch of single simple inputs. Let me say that's good. So we have our last one there. What do we do? I'm going to bring it down here. Natural log of the fourth root of xy over ez. So which rules apply? Do we have a product rule? We do, the xy and the ez. Do we have a quotient rule?
Yes.
Yeah, because there's a fraction. Do we have a power rule?
Yes.
Yes, because the fourth root of a number is the same as x to the 1/4. So perhaps the first thing we want to do is just rewrite that as natural log of xy over ez to the 1/4. So now the question is, how do we start unpeeling this thing? How do we start simplifying it down? And again, you might say, okay, what do I do first? The product rule, the quotient rule, or the exponent rule? You might once again consider, if I had the expression xy over ez to the 1/4 equals a number, like 7, what's the first thing you'd have to do to both sides? You'd have to get rid of that exponent. You'd get rid of the exponent in this context by raising both sides to the 4th power, because that way you're multiplying 1 over 4 times 4 over 1, it simplifies out, and you end up with just xy over ez equals 7/4, whatever that is. So the point is, you have to get rid of the exponent first. If you're trying to solve this algebraically, you get rid of the exponent first. So the first thing we want to do is get rid of the exponent. Or just bring it out front as the power rule. So now we have 1/4 natural log of xy over ez. Then what? What's the next thing you would do to this expression if you're doing it algebraically? You'd want to what?
You want to do the quotient rule. So what you're going to do is remove the denominator.
Yeah, we want to do the quotient rule next because algebraically, the next thing we want to do is multiply over the denominator because we want to get rid of fractions. So we'd want to get rid of the denominator next algebraically, so let's get rid of the denominator now by doing the quotient rule. So now again, brackets, we would say, okay, now this is the natural log of top minus natural log of bottom. And we put in those brackets because we want to make sure that we're still multiplying the 1/4 by the whole thing. Now what? Yeah, now the only thing that's left is the product rule. And again, proper use of parentheses. Each one of these things, I'm going to put in brackets so that I'm going to say, okay, this is 1/4, and then I have a minus. I've got something minus something. So the first natural log of xy becomes natural log of x plus natural log of y. Over here, the natural log of ez becomes the natural log of e plus the natural log of z. And I put both of those in parentheses because I'm about to subtract this parenthesis. So now we have 1/4 of natural log of x plus natural log of y minus, what's the natural log of e? This is a great question. Yeah, everybody take a look at this. Natural log of e. Now, first of all, you can type that into your calculator. E is just a number, it's not a variable. So you can look at this again and say, well, natural log is log base e of e. So e to the what is e? Yeah, that's 1. E to the what is e? 1. Another way of looking at that is you can say, well, what is the log base e of e? I don't know. I'll call it x. And then I'll rewrite it as left to the right equals middle. E to the what equals e. And it would have to be e to the 1 equals e. So the answer is 1. So we have 1/4 natural log of x plus natural log of y minus 1 minus natural log of z. And we're done. That is as simplified out as it's going to be. And again, what did we accomplish? Instead of one natural log with an incredibly complex input, we now have a bunch of natural logs, but each one only takes a single simple input, which in some context could be valuable. So all of those examples right there, 1, 2, 3, 4, that's what we would call expanding a logarithm. And I hope that's obvious why I would use the word expand. Because you're taking something incredibly condensed and then stretching it out into a long expression. Right? This was very condensed. All those symbols were condensed in one spot, and then we spread it out and we expanded it. So if examples 1 through 4 were expanding a logarithm, what are we going to do now? We're going to shorten it. We're going to condense it back into a single logarithm. So examples 5 through 8, we're going to condense some logarithms. Well, this is kind of fun. So we still want to be thinking about our rules over there, but now we have to think about them in the other way. All right, so I've got a log plus another log, and so that's going to turn, if I have a log plus a log, that's going to be a log of the product. And you know what might be helpful now is for, this might seem really simple, but it could be really helpful, is to literally write the formula backwards. So we could also say log of A plus log of B equals log AB. I realize all I did is just write the equation backwards, but it might be helpful to actually see it so you could say, oh yeah, anytime you add two logs together, it's really the log of that product. Or likewise, write this formula backwards. If you have log A minus log B, anytime you subtract two logs together, you make a fraction, log of A over B. And if you have a coefficient in front of a log, you can always take that coefficient and put it up on top as a power. So that could be helpful to just write the formulas backwards so you can better see how to apply them. So what's the first thing that we could do? If you're, we're just reading from left to right, like PEMDAS. What's the first thing we do? We'll combine those together. Log of x plus log y is log xy. Yeah, and then anytime you see a subtraction of two logs, you can turn them into a fraction. So then you'd have log base 2 of xy over z. And you did it. It's condensed. Now it's all condensed into one tiny little log. Instead of lots of logs, you just have one log. Now, I want to show you a shortcut. I mean, I don't know how quickly I should show you a shortcut, but this is pretty exciting, and I think it's helpful. For any log that you see, if the log is positive, like this one's positive, that one's negative, any positive log, that term goes in the numerator of the resulting expression. So this log was positive, so the x goes in the numerator. This log was positive, so the y goes in the numerator. This log was negative, so the z goes in the denominator. And that's a general rule. So I'm just going to write a quick example here. Let's say that I had log 2 plus log 3 minus log 4 minus log 5. And I want to really quickly condense that into one logarithm. I don't have to sit here and think about the product rule and the quotient rule in a lot of depth. I can just say, well, any positive log, that number goes in the numerator. This is a positive log, that number goes in the numerator. This log is negative, so that number goes in the denominator. And this log is negative, so that number goes in the denominator. And that's just a quick way of applying the rule. A positive log, that number goes in the numerator. A negative log, that number goes in the denominator. And so I've now condensed that pretty quickly into 6/20ths or log of 3/10. Which could even go down to log of 0.3. And I think we'd all agree that's much simpler. Instead of having to sit there on your calculator and type log 2 plus log 3 minus log 4 minus log 5, you could just type log 0.3. And it's going to give you the same answer. So let's apply that. We have a positive log, a negative log, and a negative log. So we can apply this rule. Now the first thing is the coefficients have to become exponents first. So I've got this 1/2 in front of the log. That 1/2 has to go up on the x, so it's x to the 1/2. And this 2 is in front of the log. The 2 has to go up in front. I'm sorry, on top of the y, so it's y squared. So start by rewriting it. This is really log base 3 of x to the 1/2 minus log base 3 of y squared minus log base 3 of z. And now I clearly see that I have a positive log, so that term goes in the numerator, a negative log, so that term goes in the denominator, and a negative log, so that term goes in the denominator. And what am I left with? Log base 3 of a fraction. Then you place those terms into the numerator or denominator, depending on whether or not it's a positive log or a negative log. By the way, what's x to the 1/2? Square root of x. So this is a positive log, I'm going to put root x in the numerator. This is a negative log, I'm going to put y squared in the denominator. And this is a negative log, so I'm going to put z in the denominator. And that's it. I have to admit, I love mathematics. I can't help it. I love it. I love it. I just love it. So I don't necessarily, I'm like, oh, great, this is all so much fun. This is fun. But I also realize that from your perspective, watching all this, it might seem like I'm like, okay, now, just remember in mathematics, whenever you're rubbing your tummy, you pat your head twice. But if you pat your head twice, you have to stomp your foot 3 times. And then, but if you stomp your foot 3 times, then you have to do a little quick shake, And like, you look at all these rules, and after a while, you're like, what is happening? What is the purpose of all of these rules? And I'm like, well, it doesn't really matter. Just keep tapping those tummies. But so I realize as I sit here and share this with you, that you might be thinking to yourself, this is all pretty arbitrary. I mean, does anyone feel that way? Or am I just making this up? Is everybody just fine with this? You're like, great, more rules. I'm happy. Or maybe you're like, this all seems pretty out there. It's true. No matter how far you go in mathematics, you're always going to reach some point where you're like, oh man, these rules seem so arbitrary. Why are we even doing this? What's the purpose? The point is, it serves a purpose further down the road. We learn all these tools because at some point it's going to help you solve an application problem. Okay. So every once in a while, I just try to empathize with you. That's what I just did. I just empathized with you. This might seem weird, and so I'm empathizing with you. Okay, how about the next one? We have an expanded log expression. We want to condense it down to 1. The first thing we always have to do is put those coefficients on top as an exponent. And then we can proceed to condense it into a fraction. So this, now by the way, what kind of a log is this? Log base 10. So we have log x minus log z to the 1/3 plus log y to the 1/2. Because we bumped those exponents up on top. And by turning those fractions into exponents, we can now also rewrite it as log x minus log cube root of z plus log square root of y. And again, as before, any positive log, that term goes in the numerator. Any negative log, that term goes in the denominator. So my x goes in the top, my cube root of z goes in the bottom, and my square root of y goes in the top. Yeah, like with a skill like this, you might think, okay, well, I mean, it's not that hard. Why? Why would we do something like this? And again, there's a certain power mathematically that comes from being able to manipulate expressions to change their form. Okay, now how about this last one? We have log base 7 of x, log base 7 of x minus 3, and then the number 2. What do we do with that number 2? Do we have any log rules over here at all that say what happens if you just add or subtract a number?
You just keep it outside.
What's that?
Put it in parentheses, combine first, log 7s first, and then after that, keep like a parentheses out and put the negative out. Good too.
Yeah, I mean, we could certainly go ahead and combine these two together first, right? We could go ahead and say, well, at the very least, I know I'm adding these two logs together. They're both positive, so that's going to become log of x times x minus 3. And that's my first log expression. Then I still have a minus 2. And you might say, leave the minus 2. Who cares about the minus 2? It's minus 2. That's not hard. You can always just minus a 2 from whatever you do. But what they really want us to do is condense this into one logarithmic expression. So the question is, this is a good question, log base 7 of x times x minus 3. How can I rewrite the number 2 as log base 7 of something? I would like to rewrite the number 2 as a log. First time you see this, it could wrinkle your brain a little bit. I want to rewrite the number 2 as log base 7 of something. So what number do I have to put there so that this expression would equal 2? Well, we could put x, but we want an actual thing. We want an actual number right there such that log base 7 of that number will equal 2. What number do we put there? This is a good tricky question. Let's try 2. Would that work? 7 to the what is 2? 7 to the what is 2? Does that mean the answer is 2? Is 7 squared equal to 2? Well, 7 squared is equal to 49. So what number should we put right here? Evan? You could try 21. If we did 7 to the what is 21? 7 to the what is 21? I don't know. Probably 1.3 or something like that. But it's not 2. We need 7 to the something. 7 to the what? No, wait. 7 to the what would equal this number, and I want the what to be a 2. Let's try 49. How about that, folks? 7 to the what is 49? 2. So yeah, this is correct. We rewrote the number 2 as a log. Now that's a little bit of mind-blowing right there. So what I'm telling you is that you could take something simple like 2 plus 3 equals 5, right? Something really fun, something simple from elementary school. 2 plus 3 equals 5. And I can say, well, 2, that's actually log base 7 of 49. And, well, do I know 7 cubed? Yeah, 243 maybe. So then 3 is really log base 7 of 243 equals log base 7. I don't know 7 to the 5th. Okay, that was not the best example because it's log 7. Let me write it down real quick. Or that is, let me get it down. 7 to the 5th. There we go. 16807. There. I took the very simple expression 2 plus 3 equals 5, and I changed 2 into log base 7 of 49. Because 7 to the what is 49? 2. I turned 3 into log base 7 of 243 because 7 cubed is 343. And then I turned 5 into log base 7 of 16807 because 7 to the what is 16807 5. So now I have here this, I rewrote 2 plus 3 equals 5 into a bunch of nasty logarithms. Why would anyone want to do that? Just for no good reason. The point is now that we rewrote 2 as a log, and so now I can condense these two together as well. This is a positive log, this is a negative log, so I end up with log base 7 of a fraction. The positive log goes up top, x times x minus 3. The negative log goes in bottom, and that's 49. That's what we've done. We've condensed the log into a single log. That's the goal in all of these, is to condense the expression into a single log. And that was pretty cool how we were able to flexibly turn the number 2 into an expression that was log base 7 so that we can combine it with this other log base 7. Yeah, so thank you, Andrew. You're saying the final answer? Yeah, so the final answer now is x times x minus 3 all over 49. And it seems like more computation. Let's count the computations. You first subtract 3, multiply by x, divide by 49, plug it into the log. So that's 4 computations. Up here, I'd plug it into the log, subtract it by 3, plug it into the log, and then subtract it by 2. Actually, that's 1 computation, 2 computations, minus that and add that. This is actually 5 computations, whereas this is only 4 computations. Yeah, you know, I mean, it really all just depends. The point is, folks, you've now seen how to manipulate a logarithmic expression and rewrite it. So, let's go ahead and move along. Any questions from any of that, folks? How important is it that you have these log properties written down somewhere so that you can look at them and remind yourself? I think pretty important to have those written down. Okay. They want us to evaluate these expressions. All right, well, that seems fun enough. They're telling us what A, B, and C are, and they want us to apparently plug this into a calculator. First of all, folks, do you know the quick and easy way to deal with a negative exponent? I'm forgetting now if we talked about this in this class or if it was another class. A negative exponent means push. So b to the negative 2, if it's in the denominator, you can push it to the numerator as b to the positive 2. A to the negative 1, a negative exponent means push. If it's in the numerator, you can push it to the denominator and the exponent becomes positive. So watch this real quick. I have natural log of that expression. Anything that's negative, I can push it to the other side of the fraction to make the exponent positive. So my a to the negative 1 becomes a to the positive 1 in the bottom. My b to the negative 2 becomes b to the positive 2 in the numerator, and my c cubed stays c cubed in the denominator. That way they're all positive exponents. I think that's something worthwhile to know. I'm not saying we're definitely going to use that in doing these computations, but it's worthwhile to know. Now, to be honest, I feel like the fastest way to do this would just be to plug in the numbers right now and calculate it. I'm not sure if they want us to expand this, because like if they really wanted us to, we could expand this into natural log b squared minus natural log of a minus natural log of c cubed. And notice what I just did there. Anything that was in the numerator, I made a positive log, and anything that was in the denominator, I made a negative log. So that's applying the rule that we were just doing. If I really wanted to, I could do that, and then I could bring those exponents out front, and I could call this 2 natural log b minus natural log a minus 3 natural log c. And there would be a fully expanded expression of what they gave us originally. And then we could plug in the 2, 3, and 5 for a, b, and c and calculate it all. But honestly, they've given us no other instructions. They just want us to evaluate it. We can just go ahead and plug in the numbers now. And then plug it all into the natural log. So what do we have here? Natural log of b squared, 3 squared is 9. All over a, that's 2. C cubed, 5 cubed is 125. And so this is really the natural log of 9 over 250. You can just plug that into your calculator. So everybody try that. This is some good practice on your calculator. Everybody has to find the LN button. It should automatically give you a parenthesis and then type in 9 divided by 250, another parenthesis. And I got negative 3.32. Now remember, on the Moore website, they typically want 4 decimals. If you're going to do decimals, you normally have to have 4 decimals. 3242. So did we even have to rewrite the log? No. If we did rewrite the log, would we get the same answer? 2 natural log of 3 minus natural log of 2 minus 3 natural log of 5. Yeah, I got the same answer either way. And perhaps that's part of the point, is to see that whether you keep it condensed or you expand it, if you plug in some numbers, you should get the same answer either way. Perhaps they intend this to be like proof that all these properties really do work. Okay, so folks, how can we rewrite this one? I want you to use the push idea. Oops. How do I rewrite this so that there's no negative exponents? By the way, have you ever heard a negative exponent be associated with the word push? I think I might have just made this up. Like in some previous class, I just like the word push. But it just means pushing it from numerator to denominator, denominator to numerator. So if I saw this expression, b to the negative 1, c to the negative 1, a to the negative 4, I know that I can push those into the denominator. I would immediately make the denominator of 1 so that I can actually see now what to do with all those terms. And so now what I'll do is I'll write natural log the square root of 1 over b, c, a to the 4. And all we did so far is just push all those terms into the denominator so that we have positive exponents. And now we can go about plugging in those numbers that they gave us So b times c times a to the fourth. So that's 3 times 5 times 2 to the fourth, which I got 240. And so the natural log of the square root of 1 over 240. This would be a good one for you to practice plugging into your calculator. The natural log of the square root of 1 divided by 240. Just so you all see what that looks like on your calculator, it should be natural log parenthesis, square root parenthesis, 1 divided by 240, parenthesis, parenthesis. Again, you really could have a whole course called parentheses and how to use them. Did anyone else get negative 2.7413? Okay. So how about that last one? What should we do with this negative 2? That negative 2 is on the entire denominator. What could we do with it? Yeah, this whole term can get pushed into the numerator now with a positive 2. So that's one option. I can rewrite this whole thing now as natural log of, now notice again this b negative 3. I can rewrite this expression as a cubed over b cubed. Because that's really a cubed b negative 3 over 1. And so I can push that b to the negative 3 to the denominator. So now I have natural log of a cubed over b cubed. That was the first part. And then down here I have this whole expression being raised to the negative 2. So again, a negative exponent means push. I can push that entire expression up into the denominator, or up into the numerator. So now I have a natural log of a cubed over b cubed times natural log of bc. And I don't have any more negative exponents. You can say the entire purpose here is to learn how to get rid of negative exponents. Because really people don't like negative exponents. A negative exponent is really just a placeholder for you to move that object into the opposite side of the fraction and then compute the exponent. So there we have it. Now you plug in all of your numbers. That's a cubed over b cubed times the natural log of b times c. And you plug both of those into your calculator and you'd be done. Okay. Oh boy. All right. Folks, we're just about done with this. I feel like we're just kind of, we have to be exposed to this and see how to work it all, but we're about to get back to solving actual equations. What did anybody get? Did anyone else get negative 3.29? Or now it's 4059. So in the Moore program, if you wanted to round it to 4 decimal places, that'd be what? 294. What, Evan?
It shouldn't be BC squared.
Oh, thank you. That is not the right answer. Thank you, Evan. It should be BC squared. My goodness. Thank you. So that's going to change my answer considerably. And then a squared. Okay, I got negative 8.9205. Thanks, Evan, for catching that. All right, so everything we've just done so far is in the service of knowing how to manipulate a logarithmic expression. These were just a bunch of tools that we just did, and we're going to apply these tools more specifically when we're actually trying to solve equations. That is, solve for x, which is always what we do in math. All right. Super. This next formula is critical. It's called the change of base rule and the change of base formula, and it allows you to compute any log base in your calculator. So let's take a look here at log base 3 of 12. Does your calculator have log base 3? No, other than Emily and a few others. So no, you don't have log base 3 in your calculator. So how could you compute this, log base 3 of 12? You can all compute this. It's just very time consuming and laborious. How would you compute it? You'd have to say 3 to the what is 12. And you could sandwich it. 3 to the 2 is 9. And 3 to the 3 is 27. So I know the answer has to be between 2 and 3. So then the way you would go, just starting to guess. So maybe it's 3 to the power of 2.5. And you start trying to zero in on what the actual answer is. It's not very fun. You know, using the sandwich technique to start guessing what the power of x would need to be. But so far, don't we know the answer should be roughly 2.5? You know, somewhere in the neighborhood? So let's just keep in mind our guess is 2.5. 2.5? Something like that. That's what our answer should be. So at least we have a ballpark answer. Log base 3 of 12? Oh, it's like 2 something, right? Okay, so the change of base rule. Take a look at it up here. It says that if you have the log base a of x, where a is some number other than 10 or e, because your calculator already knows how to do base 10 or e. So if you have some base other than 10 or e, you can rewrite it as log of x divided by log of a, where this log is the log base 10. You might want to jot that in, that it's log base 10. So this is something your calculator can do. So you take any log base, something that your calculator can't do, and you rewrite it as log of the argument divided by log of the base. It might be helpful to write those out. This is the base. This is the argument. I use the word argument, not like something you have with your spouse. I mean the input. Argument is another word for input. So, and just so you know, it doesn't have to be base 10. It can actually be ln of x over ln of a as well. You can use either of the buttons on your calculator. You can either do your log button or you can do your ln button. They're both going to give you the same answer. It's pretty wild. So let's try it. I want to know what log base 3 of 12 is. Simply speaking, you do the log of 12 divided by the log of 3. And that's it. That's the change of base formula. That's how you are able to compute a base other than 10 using your calculator, is by doing a two-step process. So go ahead and do that on your calculator. Make sure you use a lot of parentheses. So there's going to be parenthesis log 12 parenthesis divided by parenthesis log 3 parenthesis. Just so you see what I typed in, I typed parenthesis log 12 parenthesis divided by parenthesis log 3 parenthesis. You see how many parentheses I have there? The answer is a lot. I wrap the argument in parentheses, I wrap the log in parentheses, and then I compute all that. So what did you get? 2.26? 19? Rounding to 4 decimal places? Is that pretty close to our original guess? Yes. Yeah, sure is. And that's called the change of base rule. It allows you to compute any log base on your calculator simply by dividing the log of this number divided by the log of that number. Very powerful. So like log base 5 of 80, your calculator won't do it. I could do a sandwich theorem real quick and say, well, 5 squared is 25, and 5 cubed is 125. So the answer I'm looking for must be between 2 and 3. I'm going to guess it's actually 5 to the power of 2.6. Sure, why not? But so now I'll use the change of base formula to actually compute that. So it's log 80 divided by log 5. And I'm going to go back in my calculator and just hit second entry to pull back up the previous expression I already had, so I can just edit it. So it's log 80 divided by log 5. And I get the answer 2.7227. Now, folks, I hope you just memorize this and becomes muscle memory, the order of these numbers. I always look at it like this. That 5 is teeny tiny and technically lower than the 8. So where does it go? Into the denominator. And that 80 is big and above the 5, so it goes in the numerator. So visually, it kind of reminds you where to put the numbers. everyone feel about the change of base formula? Oh, goodness. All right. One thing that I think is worth showing you, because it's fun. Because right now I just presented that change of base formula to you like it's magic. Like it's out of the Harry Potter books. Like, oh, you just divide that by that, and then it gives you the answer. Like, I mean, that's just sheer magic. So you might ask yourself, well, how does it really work? So I want you all to watch. I'm going to show you the proof of the change of base formula. It's really simple, and it's really straightforward, and it's worth seeing. So let's say I wanted to know what log base 3 of 12 was. And again, I'm going to show you this technique. It's a very common technique in mathematics. I say, okay, log base 3 of 12. What is it equal to? And so I write equals x, because I want to know what does it equal. So watch, everybody watch. Are you all watching? All right. So what's the first thing I can do? I don't know how to actually compute this, so I'm going to convert from log form into exponential form. This is going to be a theme for the day. Whenever you're given an expression and you don't know how to solve it, just convert it into the other form. So we're always going to go back and forth between log form and exponential form. Remember, exponential form would be like 2 to the 3 equals 8. Log form would be log base 2 of 8 equals 3. Being able to convert back and forth between these two forms is fundamental to solving logarithms. So I'm going to convert this from log form into exponential form. That means 3 to left to the right equals middle, 3 to the x equals 12. Now I converted this form, and you might say, well, you're no further along than you were before. You still don't know what 3 to the power of what is 12. After all, we already knew that's what the question was. 3 to the power of what is 12? Now I've just written it as 3 to the what is 12. How does that help me at all? Well, in algebra, and this is so important, I've got goosebumps right now that I get to share this with you. In algebra, what are you allowed to do? I can add something to both sides. I can subtract something from both sides. I can multiply something to both sides. I can divide something from both sides. I can square both sides. I can square root both sides. I can do anything I want so long as you do it to both sides, right? So watch. I can take the log of both sides. This is so cool. I'm allowed to just take the log of both sides. Which log? Log base 10. Because log base 10 is something my calculator knows how to do. And so this falls under algebra. You're allowed to do anything you want so long as you do it to both sides. I just took the log of both sides. Why? Because I can. So now what? Notice where my x is. It's an exponent. What rule applies? The power rule applies. I can bump that x down out front, and now I just have x being multiplied by log 3 equals log 12. What's my goal all along? To solve for x, to figure out what x is. X is being multiplied by log 3. What do? Divide by log 3. And what did we find out? X is equal to log base 10, something my calculator knows how to do, divided by log base 10, something my calculator knows how to do, of 3. And therefore, hold on, let me go back. Log base 3 of 12 is equal to x, which is equal to log of 12 over log of 3. So by doing some fairly simple, straightforward algebra, I was able to show why the change of base rule works. So what did we do? We took a logarithmic expression that was in a base our calculator couldn't do. We rewrote it in exponential form. And then I took the log of both sides. Why? Because we can. Because that's algebra. There's such freedom in algebra. You can do anything you want so long as you do it to both sides. And then I used the power rule to bump the x out in front. Log 3 is just a number. I divide it off to the other side, and boom. We have a proof of the change of base formula. Okay. So folks, I know my phone just went off, and that's a perfect time to take a break because we're about to start the bread and butter of this chapter. Going all the way back to the beginning of talking about logarithms, remember how we started class? I said 10 to the power of what is equal to 50. And we introduced this word logarithm, which means solve for the exponent. So now look at this equation right here. You don't get any more basic than this. A number raised to what power will equal another number? This is the fundamental question of logarithms, right? This looks very different from, say, 6 times x equals 1573. If it was 6 times x equals 1573, we already know how to solve that just through algebra. Divide both sides by 6. This is a very different problem. And it wasn't until the 1500s that they figured out how to solve these problems, right? People have been solving these problems all the way back to ancient Greece, 500 BC, 1000 BC, 2000 BC. I mean, people have known how to solve this for a long time. This was solved in the 1500s by John Napier and the invention of logarithms. So this is what we're going to do when we come back. Oh boy, I'm sure everybody's just on the edge of their seat. I'm not going to put alarms for again. Let's come back at 9:13. I happen to be free today beyond my walk settings, so I'm in my but I'm here until probably this afternoon. So where do you do it? Oh, okay. This is here on campus. I'll tell you where you are. Okay, everything. Yeah. Well. This Friday I had a pivot schedule for time. Yeah, because you mean Friday you could be out for 3. You did 2:45. Oh, you can? Oh, okay. You're at 5 right now? I'm sorry, maybe I didn't notice that. Okay, well, let me pencil that in then. Okay, Jerry, I put Friday at 2:45. Oh, you're not missing. Hi there. Come on back, folks.
Whole quarter.
All right, folks. Let's try this next problem. Where's everybody else? All right, folks. Let's dive into this next problem. Very, very exciting. This is the whole purpose of logarithms. You're about to start a whole new branch in your life, understanding how to solve exponential equations. So first of all, this problem says 6 to the what is 1573. So I'd like to point out, you have a tool available to you to solve that problem. It's just long and laborious and tedious and no one likes it. So if I said, well, I want 1573, I've already sandwiched that between 6 to the 4th and 6 to the 5th. So I know my answer so far is k equals 4 something. All right, that's as much as I know. K equals 4 something. And that's helpful. That at least tells me that whenever I'm done doing this process, I can check my answer. Well, I can check my answer in a lot of ways, because whenever we finish solving for k, you should be able to take that, plug it back in, and do 6 to the power of that answer, and you should get 1573. So you can always check your answer, but that was my sandwich beginning, just to put me in the ballpark. Okay, so we want 6 to the k equals 1573. What do? There's a couple techniques we're going to use over and over again. So, techniques. Number 1, convert from log to exponent, log form to exponential form, or exponential form to log form. All right, that's one particular technique that we're going to use over and over, is just convert from one form to the other. So this is exponential form, so let's convert to log form. So log form would be log base 6. Remember, to write it in log form, the first number stays the same, that's the base. Log base 6 of 1573 equals k. So that's just purely switching from exponential form to log form. And at this point, we're already done. Because if you're like Emily, you can just type that expression into your calculator. And if you're like anybody else, you can do the change of base formula, and you can change this to log 1573 divided by log 6. Both of those are base 10, and we have our answer. So we go ahead and just type it into our calculator, again, using lots and lots of parentheses. Log 1573 divided by log 6. And I don't know about you, but I got the answer 4.108107159, ... How many decimals are in that answer? Okay, infinitely many. There are infinitely many decimals in that answer. It's an irrational number. Typically, when you take a log, you get an irrational number. Remember what that means? It's a decimal that goes on forever without repetition. So that decimal would just keep going and going and going. For the more program, you can probably cut it off at 4.1081. And that is in the ballpark of what I originally thought. I knew that the answer would be 4 to something. And now check your work, because remember, at this point, we've just done some algebra. We haven't solved for k yet. Solving for k means you took that number and you plugged it in and you checked to make sure it worked. So if we do 6 to the power of 4.1081, you get 6 to the power of 4.1081 is 1572.979. And we call that close enough for government work. All right? I hope I'm not offending any government workers in there. That's a phrase. I've always heard the phrase close enough for government work. I don't know if that's wrong to say that. Maybe that's something I shouldn't say. Anyway, now if I had used more decimals, it would have been better. So had I done 6 to the power of 4.1081071159, then I wonder what I would have got. So 6 to the power of 4.1081071159. Woo! My calculator actually says 1573. Now that's not accurate. There's technically infinitely many decimals in that answer. The fact that my calculator gave me 1573 is round off error. It's because the calculator actually computed 1573.000000000000001, but it was like, I can't compute an answer with that many decimals, so it rounded it to 0.00000, which just said 1573. Either that or it computed 1572.99999.98, and again, it just rounded it. So don't actually think that that's the right answer. The correct answer has infinitely many decimals. That's just an approximation. Okay, well, there we have it, folks. We, using logarithms, can now solve any exponential equation, which again was a technology invented in the 1500s. Let's try another one. Here we have 20 times 1.31 to the what equals 510.
Did you, for the test, did you need rounding of 4?
Yeah, rounding of 4 is fine.
Okay.
So we have this expression here, and I'd like to remind you of an idea that we did a couple class periods ago, and that is if you have a square root formula, like let's say that I had 5 root x plus 3 minus 7 equals 20, and I'm going to solve this formula, what do I do?
The 7 over and then divide by 5.
Yeah, you'd have to move the 7 over and divide up to 5, because what are we trying to do? Isolate the root. You all remember that phrase? Isolate the root. You have to isolate the root before you can square both sides to cancel the root, right? So isolate the root. Same thing here. You have to isolate the exponential expression. Isolate the exponential. So I put a box around it. I put a little box around my exponential expression, and I say, okay, that's the thing I need to get by itself. I need to get 1.31 to the k all by itself. Before you can do anything else, you have to do a little bit of algebraic manipulation. Not a lot of algebraic manipulation. All we have to do is divide off 20. So now we have 1.31 to the k is equal to 25.5. Okay, now we can do the logarithm part. And the logarithm part is that, again, our technique is if they give it to you in exponential form, convert it to log form. If they give it to you in log form, put it in exponential form. So they gave it to us in exponential form. We convert it to log form. That's log base 1.31 of 25.5 equals k. And that expression we can type right into our calculator. And by that I mean you can type it right into your calculator using the change of base formula, which means log base 10, button on your calculator, of 25.5 divided by log base 10 of 1.31. And that's your answer. You probably want to play around with checking to make sure that you're using enough parentheses. Everyone can check your own work right now. You should get 11.99389, which I got that. Did anyone else get 11.99? Yeah. Can I just share a calculator insight? See, when you type that into your calculator, you might just type in log parenthesis 25.5 divided by log parenthesis 1.31. And when I see that, I get nervous. I cringe a little bit. Because technically speaking, anytime you use the division symbol on your calculator, you should wrap the numerator in parentheses and wrap the denominator in parentheses. It's best practice. So technically, I would encourage you to just start getting used to the idea of always, whenever you do division, put the numerator in parentheses, put the denominator in parentheses, because it's a best practice and it will serve you always. Whereas by not putting the parentheses around the numerator and not putting the parentheses around the denominator, every once in a while you're going to type in an expression and it's going to give you the wrong answer because you're not using parentheses correctly. Okay, how does everyone feel about that? Is the answer 11.9939 correct? How do we know? You have to put it back into the equation. So now I'd say 20 times 1.31 to the power of 11.9939, and it equals 510.0000147. So yes. If I convince you of anything by the end of this semester, by December or whatever, you take your final exam and you leave this class, I hope I've convinced you that I'm a really funny guy. No. I hope I've convinced you, oh yeah, that you're not done solving for x until you plug the number back into the expression. Because if you just get to here and you like say, okay, great, I'm done. No, you're not really done. You could be wrong. Your answer could be wrong. You know, you wouldn't leave it to chance. You know, if you're a doctor and you're going to perform surgery, I sure hope you don't just solve for x and be like, that patient needs that many cc's of medication. Please plug it back in and check. Right? Don't just say, oh, I did the algebra, so my number's right. All right, let's do some more. So here we are, section 6.3, and we're just going to now solve a whole bunch of equations. Again, this is the bread and butter of algebra. In algebra, we solve for x. That means find a number that you can plug into the equation that makes the equation true, and it just so happens that all of these equations have exponents where the x is located, which means we need a logarithmic expression, which also means that in order to solve for x, there's a good chance we're going to need some of these tools. So these tools, you know, they were kind of all fun and dandy when we're just, you know, condensing and expanding log expressions, but they might actually turn out to be really critical here in our ability to solve for x. So what does it say? Steps for solving an equation: isolate the exponential function. Hey, that's what we already know. Isolate the exponential expression. If convenient, that's hilarious. Express both sides with a common base and equate the exponents. Okay. Or otherwise, take the natural log of both sides and use the power rule. Okay, well, both of those are just fine. We'll look at a variety of ways of solving problems. So, notice that the very first option says, if convenient, express both sides with a common base. So, let's take a look here at 5 and 125. Again, you've all been practicing your bases. Counting by 2s, 2, 4, 8, 16, 32, 64, 128, etc. Counting by 3s, 3, 9, 27, 81, 243. You've all been practicing this at home, right? Counting by 5s, 5, 25, 125, 625, 3,125. You've all been practicing this, right? So what's the number 125? 5 to the 3, yeah. Yeah, so 125 is actually 5 to 3. Everybody write it down. This equation is actually 5 to the 2x minus 1 is equal to 5 to the 3. The only way this becomes obvious is if you're actually building your familiarity with powers of numbers, which means looking at those numbers and reciting them. Like right now, we're working with my 2-year-old daughter to learn how to count to 10. And man, every single time she says 1, 2, 3, 4, 7, 8, 9, 10. She skips the 5, 6 every time. And like when I say it to her, I really emphasize the 5, 6. I'm like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But she still doesn't do it. The point is, I'm sure she'll get it eventually. But folks, the only way you're going to recognize these numbers is if you practice. You have to practice them. Okay, so part A says, if convenient, express both sides with a common base and equate the exponents. So we have 5 to something equals 5 to something. The only way this equation works is if this is equal to this. So we now write 2x minus 1 must equal 3. By the sheer force of logic alone, 2x minus 1 must be equal to 3. Because otherwise, these two sides of the equations are not going to be equal. And then you do some algebra, add 1 to both sides, divide by 2, and we get the answer x equals 2. Now this was neat. Did you have to use any logarithms? None at all. Now, alternatively, how else could we have solved this problem? Yeah, exactly. They gave it to us in exponential form. You could convert it to log form. Try this again. Here it is in exponential form. I'm going to convert to log form. Log base 5 of 125 equals 2x minus 1. And now just looking at this, you should all be able to say 5 to the what is 125? 3. And here, the exact same formula falls out. 3 equals 2x minus 1. Again, we have 2x equals 4, and again, we have x equals 2. Now, which way was better? I mean, both ways are just fine. You know, if you happen to recognize 125, then you can just use your number fluency to rewrite it as 5 cubed, and you can just solve the equation, and there are no logarithms required. If you don't recognize 125, then you automatically have to do more advanced mathematics. But look, you still are going to have to know 5 to the 1 is 125. There's no way to get around it, right? Unless you just use your calculator. You can type that into your calculator as log 125 divided by log 5, and it will tell you 3. But I really hope that you're just working on building your number fluency to recognize the number 125 is 5 cubed. Okay, next one. What are the 2x equals 1/2?
I have a question.
Yeah.
Sorry. Because of the technique before, you said if you were to log both sides, like log of 5, log of 125, you have the exponent x to 1, bring the exponent to the side, and divide both sides. Would that prove it out the same way, right? Or is
that would still totally work, folks. Just to show one more example of, and in fact, that's technique B. Take the log of both sides and then use the power rule. That would be far more complex than is necessary in this situation. But if you had 5 to the 2x minus 1 equals 125, again, because algebra says you can do anything you want so long as you do it to both sides, I would take the log of the left-hand side and the log of the right-hand side, and then use the power rule to bring the 2x minus 1 out front. So now I have 2x minus 1 times log of 5 equals log of 125. And now how do I solve for x? I'll divide off the log 5 first to get the x by itself. So now I have log 5 over here. And now I have 2x minus 1 equals all that. As soon as I type that into my calculator, I get 3. Yeah. And then away you go, still solving the same problem. So yeah, that is 3 techniques, isn't it? So technique number 1, which is going to be the favorite, is convert exponential to log. Technique number 2 is equate the bases. Equate bases. That's what we just did in this first one. We changed 125 to 5 so that we could equate the bases so that you can equate the exponents. Equate the bases so you can equate the exponents. Technique 3 we've seen all of them now, is take the log of both sides. Will all three approaches give you the answer? Yeah. Will all three techniques always work? Not the equate the base sides. You won't always be able to equate the bases. So this technique, equate the bases to equate the exponents, this is just a lucky technique. Sometimes it works, sometimes it doesn't. But these two techniques, 1 and 3, will always work. Okay, let's try another one. We have 4 to the 2x equals 1/2. I'd like you to see about equating the bases. Look at the number 4 and look at the number 1/2. How do we rewrite those as the same base? Like for instance, consider you're multiplying by 2's. So that's 2, 4, 8, 16, 32. Consider multiplying by 3's. 3, 9, 27, 81. Consider multiplying by 5's. 5, 25, 125. What powers are we looking at since I have the number 4 and the number 2? Yeah, I'm clearly looking at powers of 2. Right? So I want to rewrite everything in terms of a power of 2. That would be the goal. How do I rewrite 4 as a power of 2? Yeah, that's 2 squared to the 2x. And how do I rewrite 1/2 as a power of 2? That'd be 2 to the -1. All right, everyone, take a good close look at what we just did there, because that's some pretty subtle dark magic that we just did. Right? That's some leisure domain. That's some occlumency. That's abracadabra. I was trying to quote Harry Potter for a bunch of those. What's the terrible one? The Avada Kedavra? Yeah, that's the death curse. Yeah, we just death cursed that. I mean, look at it. So now what? We have 2 to the 2 to the 2x. What rule can we use there? When you have an exponent raised to an exponent, you multiply the exponents. So that's 2 to the 4x equals 2 to the -1. Look at what we just did. By some subtle playing with numbers, we now can say 2 to the 4x is equal to 2 to the -1. We made the bases equal to each other. Therefore, the exponents must be equal to each other. Therefore, 4x must be equal to -1. And therefore, x must be equal to -1/4. Now, you might say right there, Mr. G, this technique number 2, equate the bases, equate the exponents. What you're telling me is I have to, in order to use that technique, look at the numbers and say, hey, are 5 and 125 related? You have to think about 125. You're like, oh yeah, 125 is 5 cubed. This is 5. Okay, they're the same base. I can rewrite it. And then here you'd have to say, okay, it's 4 and 1/2 related. Well, I mean, yeah, 4 is 2 squared and 1/2 is 2 to the -1. Okay, yeah, I can rewrite them. Right about then, you might say, Mr. G, not interested in that game. Right? Like, I'm not interested in building this number of fluency. I'm not interested in being able to recognize the number 625. Hey, look, it's 5 to the 4. You know, maybe you're saying, that's not for me. It's just not the way my brain works. Well, that's fine, because you're still allowed to use technique number 1, which is the same as technique number 3, but I like technique number 1. So right now, I can just say this is exponential form converted to log form. So this log base 4 of 1/2 equals 2x. So we're about to solve it again, but different. You take your exponential form, convert it to log form. Now this you can just type into your calculator. So using the change of base formula, you can type this directly into your calculator and get an answer. So I don't know, you know, over the long run, you might just know how to look at that and say, okay, that's log of 1/2 divided by log of 4. You might just build that into your muscle memory. Log base 4 of 1/2, you type it in your calculator, is log of 1/2 divided by log of 4. If you want to write it down, you certainly can. That's log of 1/2 divided by log of 4. That way you can type it into your calculator, in which case you get the answer. -0.5 or -1/2. I'll put -0.5. Okay, so now I just have a very basic algebra equation. I divide both sides by 2, still in my calculator, divide by 2. X equals -0.25, which is, of course, the same as -1/4. So the real trade-off here is that if you build your number fluency, and you can recognize powers of simple numbers like 2, 3, and 5, then you can solve problems, some problems, by just equating the bases and rewriting it at the same base. Then you can equate the exponents, and you do the whole problem without using logarithms at all. Or if you don't want to build your number fluency, or you're just like, that technique, it takes too much time. I'd rather just take exponential form, convert it to log form, get it over with, do the business on my calculator, get the answer. Both ways are fine. On the test, I'm pretty sure either technique that you want to use, I'll be happy with. So long as you're showing me your work. You all know that if you just, if you see this problem, you just write down x equals 2, I'm not going to give you any credit for that. You need to show some sort of work. And so long as you're showing me one of these techniques, I will give you credit. All right. By the way, did we check either of those answers? No. Are we right? We have no idea. We could have all just made a collective hallucination and a mistake and didn't get the right answer. So let's try. 5 to the 2 times 2 is 4, 4 minus 1 is 3, 5 to the 3 is 125. Yes, that's true. And then how about over here? 2 times negative a fourth. That's, what, negative a half? So 4 to the negative a half. That's 1 over 4 to the 1/2. And to the 1/2 means square root. 1 over the square root of 4 is 1 over 2, which is what it is. So, yes, both of those answers were correct. Let's try some more problems. Oh, good. You can see number 3. Just by looking at number 3, can you equate the base? Look at the number 3 and the number 81. Are they related? Are they related? They are related. They're both powers of 3. So in this particular problem, you can equate the bases. Everybody try it. Instead of writing 81, write down what? 3 to the 4th. If you have your list here, that's 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4. So instead of 81, write down 3 to the 4th. So I have 3 to the 7x equals parenthesis 3 to the 4th to the 4 minus 2x. And again, you need to remember your exponent rule. So when you take a base, raise it to an exponent, raise it to another exponent, what do you do with those exponents? You multiply them. So now we have 3 to the 7x equals 3 to the, distribute the 4, 16 minus 8x. Is that what everyone got? Right. So now we have equated the base, so we can equate the exponents. And now I have 7x is equal to 16 minus 8x. Notice the exponential part of the equation is just gone. This is no longer an exponential equation at all. It's just normal algebra. That's the power of this technique of having number fluency to rewrite a base to be the same base, because it's no longer a logarithm problem. It's just algebra. So now what do we have? 15x equals 16 and x equals 16 fifths. Did anyone else get that? Okay. So there we go, 16 fifths. You would still have to plug that in, and you can plug that in using your calculator. I'm going to plug it into your calculator, but you would just type 3 caret parenthesis 7 times parenthesis 16 divided by 15 parenthesis parenthesis. That's the left-hand side, 3 to the power of 7 times 16 fifths. You hit enter. And then the right-hand side, you plug it into your calculator, 81 to the power of parenthesis 4 minus 2 parenthesis 16 divided by 15 parenthesis parenthesis. I want you all to notice that these calculator skills of how to type this in, that's the exact same way you type it into an Excel spreadsheet. So these are skills that you can use in either context. Knowing how to type it into your TI-82 is how you type it into an Excel spreadsheet, which is how you would type it into Quicken or any other software that's out there. They all speak the same language. They all speak the language of PEMDAS. This is the language of PEMDAS right here. It's a universal language in every country you go to. So that's a good skill to be able to write things down in PEMDAS. All right. How about the next problem? 3 and 5. Are those numbers related? Are 3 and 5 related? No. There's no way to rewrite these in the same base, so there's no way to use technique number 2. Rather, we're just going to use technique number 1, which is if they give it to you in exponential, write it in log. If they give it to you in log, write it in exponential. So this is definitely given to us in exponential, so we rewrite it as logarithmic, log base 3 and 5 equals 2x. Again, maybe you're comfortable now just typing that directly into your calculator. It's log 5 divided by log 3. If you want to write it down, you can. That's log 5 divided by log 3. Keep in mind that when I just write log, that's assumed base 10. So now I have log 5 over log 3 equals 2x. Now, an important note about when to round. Because if you type log 5 divided by log 3, you're going to get a lot of decimals. Do you round now? No. You only round at the very end of the problem. So if you wanted to write down something, you have to write down all the decimals. 1.464973521. You might say, oh, Mr. G, that's so boring. Oh, so boring to write down decimals. And the next step, you divide by 2. Well, the important thing is it's still on your calculator, right? So maybe it's not so important to write down all the decimals on your paper, but you better keep all those decimals still on your calculator. Because now when you divide by 2, you still have all the decimals there, and you're getting the full accuracy of 0.7324867,604, and so on. And in the more program, you'd want 4 decimals, 0.7325. Are we right?
Mm-hmm.
Oh, good. How do we know we're right? 3 to the power of parenthesis 2 times all that. And yeah, it equals 5. All right. We've seen now how to use technique number 2, number fluency, equate the bases to equate the exponents. We've seen how to use technique number 1, convert from log to exponential or exponential to log. And now we're going to take a look at number 3. Because right now, we can't really convert this. You know, we have exponentials on both sides. There's not a single exponential expression. You know how they say to isolate the exponential? Well, you have 2 of them. So we can't really, in this case, just convert it to log form. Could we? I mean, maybe this would be log base 3 of 2x equals x minus 1. I suppose that would work, and then you could bring the x out front and get log base 3 of 2 equals x minus 1. And you could continue to work from there. So sure, you could. But it's going to be easier if we use the third technique they recommended, which was to take the log of both sides. So let's try it. Let's try this technique, take the log of both sides. Algebraically, I can now take the log of both sides. This is really interesting. I hope this blew your mind today. That algebra says you can do anything you want so long as you do it to both sides, and all your life you've been adding something to both sides, subtracting something to both sides, etc. Now you know you can also take the log of both sides. That's kind of surprising. So now what? We want to solve for x, right? So what rule can we apply? What property? The power rule. The power rule allows us to take those x's out front and make them now coefficients. So now I have x minus 1 times log 3 equals x times log 2. Well, this is good news, folks. I want you to see that this is good news, because right now, do we have any more exponentials? Is x in the exponent anywhere? No. Okay, well, that's good. Furthermore, even though we have this expression log 3 and this expression log 2, technically, if you type that into your calculator, log 3, log 2, what this really states is x minus 1 times 0.3010 equals, oops, sorry, that was log 2, 0.4771 equals x times 0.3010. Don't be writing this down, I'm just showing you. And now with this, I can distribute, and that'd be 0.4771 x minus 0.4771 equals 0.3010 x. Now, other than the fact that there's lots of decimals here, is this just basic algebra? This is just basic algebra. I would now move this number to that side, move my x over to this side, and I'd have 0.4771 minus 0.3010. I would end up with 0.1761x, move this number to the other side, equals 0.4771. And then I could divide both sides by the 0.1761, and I would end up with a very terrible decimal. 5 by 1. And I end up with 2.709. Okay. So apparently my answer is 2.709. However, I did something bad here, which is to convert to a decimal too early. I converted to a decimal too early. But I just wanted you to see that really we just have basic algebra now. Log 3 is just a number, log 2 is just a number. Everybody here can do algebra, and so you just solve for x. The difference is we're not going to convert that log 3 and that log 2 into a decimal. We're going to treat them like coefficients, which at first is uncomfortable. Like wearing plaid. No, just kidding. That's great. All right, so these are now coefficients. So let's rewrite it now as log 3, which is just a number, times x minus 1, equals log 2, which is just a number, times x. Now keep in mind what you would do if this said 3 times x minus 1 equals 2x. Would you feel weird at all about solving this? This is really straightforward algebra. You just distribute the 3 and then move the x's to the left and move the numbers to the right. And watch me go. I would just distribute the 3, 3x minus 3 equals 2x. I'd move the x's to the left, and then I'd add the 3 to the right, and I'd end up with x equals 3. Right? So, I mean, at this point, it's just standard algebra. It's just that we don't have the number 3, we have log 3. And we don't have the number 2, we have log 2. So you just have to keep that there. Let's go ahead and try it. Log 3 distribute, that becomes log 3 times x minus log 3 equals log 2x. Log 3 and log 2 are still just coefficients. They're just numbers. Just like any standard algebra, what would we do now? Where do we bring all the x's? To the left. Where do we take all the numbers? To the right. So let's go ahead and move this log 3 over to the right. So now I have log 3x equals log 2x plus log 3. Now you might be saying, Mr. G, I get it, you like parentheses. Why are you writing parentheses around log 3 and parentheses around 2, or log 2? Why am I not just writing log 3x equals log 2x? Why am I not just doing that? Yeah, that's very ambiguous. Now, am I saying log of 3x? Because that would be a totally different problem, because now the x is inside the log, which makes it hard again. The fact is, x is just a number, and log 3 is just a coefficient. So it's really important that you have those parentheses, otherwise it could get confusing. Okay, so now moving our x terms to the left, minus log 2x, minus log 2x. Now we have, I'm going to move this up so everyone can see. We have log 3x minus log 2x equals log 3. The pain is almost over. Now what? I want to do, if that just said 3x minus 2x, what would you do? You just subtract, right? 3x minus 2x is 1x. Just so you see a more formal way of thinking about it, if you did have 3x minus 2x, another way of thinking about it is that you would factor out the x and leave behind the 3 minus 2. Right? That's a little bit more formal. None of us would do it that way, but is that still correct? Yes. Right, and that's what we're going to do here. We're going to factor out the x and leave behind log 3 minus log 2 equals log 3. So by factoring out the x, now you have log 3 minus log 2. And then we want to solve for x. So we divide off that entire expression. We're going to divide both sides by log 3 minus log 2. So both sides by log 3 minus log 2. Which gives us x equals log 3 over log 3 minus log 2. That's our answer. I wish I had kept the answer from, oh, no, I did keep the answer. Previously, I said the answer was 2.7. And so now let's find out. If I do parenthesis, log 3 divided by log 3 minus log 2.
Oh, good. We get the same answer, 2.7095. Yep, 2.7095. Or maybe I should put it here. That way I can move the board back up and show you everything. So now those cancel. With x equals all that.
What is the log 3 for the top and the bottom?
Good question. Log 3 over log 3 minus log 2. Folks, if I had 5 over 5 minus 3, would the 5s cancel out? No.
Now, you might think that they do or try to, but what would that even mean? If they canceled out, what would I be left with? Something over negative 3?
What would you even be left with?
Would you cancel them and call it 1 over 1? I mean, maybe, but then you'd end up with 1 over negative 2, which is certainly not the same as 5 over 2, which is 2.5. So the answer is no. They don't cancel out.
Okay, folks, I'll be the first to admit that problem was a doozy.
Right? We've never done anything like that before in your life.
Well, unless you took a class like this before. But that was pretty sophisticated. So the best thing to do now, not cry, let's try another one. Absolutely. Yeah. So let's try it again. I'd say the only tricky part here is just treating these log things as coefficients, and if you just continue to wrap them in parentheses, you'll be okay. So let's try this again. We have 7 to the something equals 3 to the something. Notice how tricky that is. We're saying, when is 7 to the something equal to 3 to the something?
It's been a while since we've looked at Desmos. I want you to consider what we're asking. We're asking, when is 7 to the power of something equal to 3 to the power of something? So everyone take a look. When is 7 to the power of something, there's the graph, equal to 3 to the power of something? Well, they're obviously equal there, because if you raise them both to the power of 0, they're both equal to 1. But there's actually another solution. We go up here. Well, wait, is there not another solution? Oh, maybe it's the other way. Aha, I think it is the other direction. So over here. Well, it's tough to tell graphically. We know they're equal to each other there. Okay, well, I take it back. Let's just do the problem and see where it leads. What do we do? We're working now on technique 3. Take the log of both sides. So let's take the log of both sides. Log of this equals log of this. And what do we do first? After taking the log of both sides? Yeah, you get to use the power rule, which is the whole purpose of taking the log of both sides, is to bump the x from the exponent out front as a coefficient. So we get to go ahead and bump this exponent and this exponent out in front. And so now I have 3 plus 7x times log 7 equals 4 minus 2x times log 3. Now, if I can convince you of this, I'd just like you to look there and notice log 7 is just a number. It's just a decimal, 0.9. And log 3 is just a number, a decimal, like 0.3. And if I rewrote this as 0.9 times 3 plus 7x equals I'll say 2 times 4 minus 2x, could you solve that problem? Yes. Right, all of you could. It's just basic algebra. It's just instead of converting log 7 into a decimal and converting log 3 into a decimal, we want to keep that in our answer all the way down. So it just makes the algebra a little more complex. But we're still just doing normal basic algebra now. So to do normal distribution, we normally put the distributing number in front. So I have log 7 outside of 3 plus 7x equals log 3 outside of 4 minus 2x. And now we get to do a lot of distribution. So we distribute the log 7 in, we distribute the log 3 in, and what do we get? We have 3 log 7 plus 7 log 7x
And over here we have 4 log 3 minus 2 log 3 x. I appreciate you might need to sit there and stare at that for a second. Well, I didn't put parentheses around these because this is more clear. The 3 is being multiplied by log 7. You certainly can, but the real thing I want to make sure of is that I recognize that this is a coefficient in front of x. So I definitely put the parentheses on that one because I don't want anyone to think that I'm taking the log of 7x. It's 7 log 7, and you compute that as a decimal, which is, I don't know, 4.2 times x. Okay, if you're comfortable with that step, what do we do next? Just from pure theory in algebra, what are we always trying to do? You bring all your x's to the left, you bring all your numbers to the right. All your x's to the left, all your numbers to the right. So all my x's, I'm going to bring this x term over to this side. So I'm going to add 2 log 3x, add 2 log 3x over here. And what? I'll also move the 3 log 7 over to that side. I realize you can do 2 steps at once. I'm just going to leave it and do a step here at the end of the second. So I have 3 log 7. Now, right now, folks, I could write down, well, I'll just show it. So 7 log 7 x plus 2 log 3 x equals 4 log 3. There we go. So now all my x's are on the left. I still need to move all my numbers to the right, so I'm going to go ahead and subtract 3 log 7 over here. Now that's gone. And over here I have 4 log 3 minus 3 log 7. Now, what do we do with the x again? If this was 5x plus 6x, we could just add 11x, but we don't know what these are, so what can I do with the x? I factored out front. So now I have 7 log 7 plus 2 log 3. Oh boy. Again, I really realize that this might seem very, very strange at first because we're manipulating these huge log expressions. We're writing so much down. But at a more abstract level, we just have x being multiplied by something equaling something else. And so whenever you want to solve for x, x is being multiplied by this, so you, yeah, if you had like x times 2 equals 8, x is being multiplied by 2, so you divide. So we're going to divide off that entire expression to the other side, 7 log 7 plus 2 log 3, 7 log 7 plus 2 log 3. And we have our answer. X equals 4 log 3 minus 3 log 7 all over 7 log 7 plus 2 log 3. Yep. What were we trying to do again? Solve for x. And apparently x is equal to that. And if you type all that into your calculator all at once using the appropriate number of a gigantic number of parentheses, so parenthesis 4 log 3 minus 3 log 7 all over 7 log 7 plus 2 log 3. I get the decimal negative 0.0912, which might feel like a bit of a letdown. Apparently, that's the number that if I plug negative 0.0912 into the original expression, I'll get a true sentence. So let's try it. If I do 7 to the power of 3 plus 7 times negative 0.091, is that equal to 3 to the power of 4 minus 2 times negative 0.0912? Well, let's see. That's really 7 to the power of 3 plus 7 times negative 0.0991.
0.0912. That's 7 to the power of 2.3616. And that should be equal to 3 to the power of 4 minus 2 times negative 0.0912, which is 4.1824. Now, when I get it right now, you might be very unimpressed. Right? Okay, so is 7 to the power of that equal to 3 to the power of this? Well, on the left-hand side, if I do 7 to the power of 2.3616, I get 99.03382. And on the other side, if I get 3 to the power of 4.1824, I get 98.9719. What do you think? Is that close enough for government work? Do we think that these are correct? First of all, did I use enough decimals? I didn't. Because how many decimals are in this answer? How many decimals are in this answer? Infinitely many. And how many did I use? 4. Right? I mean, talk about not doing your work. Like, there are infinitely many decimals in this answer. I used 4, and what's worse, I rounded the last one. So that's not even a 2. That's actually something else. What was it? Oh no, it is a 2, but it's 2.39534. 39534. So if I redid that whole computation, but I used all those decimals, we would have seen 2 numbers that were a lot closer together. But notice, folks, what happens if I round both of these to whole numbers? If I round them both to whole numbers, what do I get? 99 equals 99, which is definitely a true statement. We're close enough within the range of accuracy of how many decimals we use. Okie doke. Well, this is definitely giving us a smattering of the types of problems you solve using logarithms. Andrew?
Type that in.
To type this? Yeah, to type that in, you just use lots and lots of parentheses. It would be parenthesis 4 log, parenthesis 3, parenthesis minus 3, log, parenthesis 7, parenthesis, divide by, parenthesis 7, log, parenthesis 7, plus 2, log, parenthesis 3, parenthesis. Was that your question? Yeah. So lots of parentheses, right? When you actually type that thing into your calculator to get a real decimal, that's how many parentheses you need to use. All right. Well, folks, there are more problems to solve. These are just a few that we've done so far. The application of logarithms to solving exponential equations is vast. And so what you have now in front of you, as you turn the page in your notes packet, there are just more and more and more problems that you can solve using these techniques. But fortunately, even though each of these might look slightly different, it's always the same techniques. You're either going to try to equate the base using your number fluency, or you can go converting from exponential to log and log to exponential, or you can take the log of both sides. And I think I heard some of you groan when I said turn the page, there's more. But unfortunately, I think that we've done the worst. I think that that was the worst. These next few ones, I think you'll find and agree with me, are not so bad. They're not so bad at all. And they're not always so bad. So let's try it. Number 7. We've got 24 minus 30 times 1.31 to the x equals negative 1941. So what's our first goal? Overall, we want to solve for x, which is in the exponent. But our first goal is to isolate the exponential. And we need to at least isolate the exponential so that we can apply one of these 3 techniques. These 3 techniques don't even begin until we've isolated the exponential. So that's kind of like first and always first, isolate the exponential. Just like you had to isolate the root. So isolating the exponential is just simple algebra. We've got this 1.31 to the x. I put a box around it so that I can just think of algebra. This thing is being multiplied by negative 30 and added by 24. So I subtract the 24, leave me with negative 30 times this box thing again, which I don't even have to bother filling it in because I use the box to represent algebra. So now I have this. And again, my box is being multiplied by negative 30, so I divide by negative 30. And now I'm left with my box equaling that. What do you think of my use of the box? I mean, that's just me being lazy, right? Because I didn't want to write down 1.31 of the x twice. But I've done it. I isolated the exponential. So now what? Looking at our techniques, can we equate the bases? No, I mean, that's not even a whole number, so it's not a power of 2, 3, or 5. So we can either take the log of both sides, or we can just convert. I think when it's something simple that it's just a pure exponential form, it's easiest just to convert. So we would call this log base 1.31 of 65.5 equals x. And in fact, we're already done, because you can all type that into your calculator. You don't have a log base 1.31 button, but you do log 65.5 divide by log 1.31, and that's the change of base formula. So just to finish showing my work, that's log 65.5 divided by log of 1.31. Although I totally appreciate if you don't actually write that step down, you might just start seeing that and just start typing it into your calculator. Either way, the answer is log 65.5 parenthesis divided by log 1.31 parenthesis. And did anyone get 15.4875?
Yes.
That was that problem better? That was not nearly as bad as all that log 2, log 3 business and distributing everything. This was just a real straightforward example. Okay. Now, you probably know this, but when you do a math class or when you read a math book, they teach you a couple formulas, a couple principles, and then they give you a bunch of exercises to do. And each exercise is slightly different from the one before it, right? And isn't that always what makes it a pain? You do one example, you move on to the next one, you're like, oh no, it's not like the last one. Right? You know what I'm saying? So every problem is slightly different, and that's because they want you to experience the full diversity of all the different ways that you can apply these formulas and rules. So this next one, it's a little different. We've got an exponential over here on the left, and we have an exponential over here on the right. And so in terms of isolating the exponential, which we said we want to do first, a little harder. But it is actually still possible. So notice this 13 isn't being added and the 11 isn't being added. But follow along with me here. I'm just going to demonstrate to you how to do this solution. First of all, if I divide the 13 over to the other side, then at least I just have 1.02 to the x over here, and that equals 11/13ths. 1.06 to the x. All right, so I've kind of gotten my numbers to the right. Now we want to bring all of our variables to the left. How could I bring the 1.06 to the x to the left? Certainly not by subtracting. Normally that's how we were doing it in the last few problems. You know, you add all the x's to one side and add all the numbers to the other side. This is not adding and subtraction. So how can I move this thing over here? By division. So now we're going to divide the 1.06 to the x over to this side. It still cancels it out, and now I have this equals 11/13. And what is that? We have an exponential divided by an exponential, to which you might say, ooh. Well, let's just remind ourselves some basic techniques regarding fractions. What if I gave you 2/3 to the power of 5? How do you raise a fraction to an exponent? You can certainly multiply it by itself 5 times. And if you did multiply it by itself 5 times and you look at just the numerator, you now have 2 times itself 5 times, which is 2 to the 5th. And on the bottom, you have 3 times itself 5 times, which is 3 to the 5th. So how do you raise a fraction to an exponent?
I mean, about this.
You just do both the numerator and the denominator to that exponent, right?
And then how about going back? What if I'm handed a fraction that has the same numerator, or sorry, the same exponent on top and bottom? I can immediately just go back to the original form and write it like this, right? So flexibly, we're allowed to rewrite this. Instead of 2 to the 5th over 3 to the 5th, I can just write 2/3 to the 5th. So what can I do here? Instead of 1.02 to the x over 1.06 to the x, I can write 1.02 over 1.06 to the x. What do we allow? Is that fair?
Yeah.
Okay. Well then, folks, at this point, we're ready to go. We have isolated our exponential expression. If you just divide 1.02 divided by 1.06, you shouldn't do that because you get an infinitely long decimal. And that would be hard to do. And 11/13, same thing. If you divide those, you get an infinitely long decimal. So you could convert them to decimals. Don't write this down and say, oh, well, this is 0.96226 to the power of x equals 0.84615. You could convert it to decimals and now finish the problem. But by converting to decimal and rounding too early, what will be true about your final answer?
You might not equate on both sides. It might not equate because if you round it too small.
Yeah, you're rounding too soon, so your answer is going to be off. So you don't want to round too soon. So we're not going to do that. And instead, we're going to keep those decimals and those fractions until we're done. So this is exponential form. We convert to log form. This is going to be painful. A little bit. Not really, just a little bit. So now this is log base 1.02 over 1.06 of 11/13 equals x. That's enough to strike terror into the hearts of many people. Right? That's log base 1.02 over 1.06 of 11/13. Right? I'm laughing because this is rough, not easy on the eyes. This is rough to look at. But it's still just log of a number and a number. So now using the change of base rule, that's just log base 10 of 11/13 over log base 10 of 1.02 over 1.06. And that is apparently what our answer is equal to. And that you can type into your calculator.
Question.
Yeah.
Couldn't you just apply the quotient rule from the top?
Could you apply the quotient rule from the top?
Meaning, once you got the 1.02x and the 1.06, and apply the quotient rule. I'm just asking the question.
Yeah,
I haven't
no, I mean,
tried it yet.
I like what you're saying, and yeah, sure. I mean, yeah, if you took
Because
the log of
now-
both sides.
Now those numbers are pretty large once you adjust them. And
Yeah.
if you broke it up in that section,
Yes, the answer is yes.
I haven't tried it yet.
You could have log 1.02 minus log 1.06 equals log of 11 minus log of 13. Yes, yes, and yes.
And then,
You divide that whole thing off, and you get log equals, or x equals log 11 minus log 13.
the possibility of you hitting the wrong numbers will be highly unlikely.
Yeah, I suppose. And ultimately,
I'm
that's
just
what
saying.
this answer is. Because now you can apply the quotient rule, and you get
Right.
the same thing.
Okay,
Yeah. All right.
sorry.
Now, folks, I'm always trying to think about your experience. And as we're going through these examples, example after example, I mean, especially after this one, I don't know if maybe you're looking at it thinking, how would I have ever known to do that? Do any of you ever think that? Like we finish a problem and you're like, how would I have ever known? What? Like that's the approach? How would I have ever known? Well, the fact is you weren't supposed to have known. That's why you take a class. You take a class to be shown example after example, example of amazing things. Like, oh my gosh, you can do that? Oh my gosh, you can do that? You're not supposed to have been able to figure all this out, right? When you take a class, you're simply being exposed to being shown miracle after miracle after miracle. Whoa, these things are possible. And the idea is now that's in your tool belt. Now that's in your tool belt. And now, every problem that you do in here becomes a new technique in your tool belt so that in the future, when you're exposed to a problem, you could say, oh, I know what to do. This is just like that problem that we did in class. So while on the one hand, this might feel like a whirlwind of confusion, like, oh my gosh, every problem is different. Well, yeah, every problem is different because you're being shown lots of techniques which you could then use to solve lots of different problems. Okay, so this particular technique, we had two exponential expressions and we combined them through division. What are we going to do here? We have two different exponentials and we're going to combine them through Well, actually, I'm not quite sure what they want us to do. Boy, that's not quite the same as that. We can't just multiply them. If it was 5 to the x times 5 to the 2x, that would have been one thing. Because then we could use the rule a to the m times a to the n equals a to the m plus n. So no, that's not quite exactly what they must be thinking that they want us to do. So what could we do? So we can't just use that rule. What could we do? Looking back at our techniques, it is honestly how you think as a mathematician. You look at your techniques, you say, well, I can't equate the bases because 5, 2, and 10 aren't all powers of the same number. I have two exponential forms which I cannot isolate, so I cannot convert from log to exponential or exponential to log. So it must be that they want me to take the log of both sides. And so you know what you do then? You just take a blind leap of faith and you take the log of both sides. Right? I'm being honest with you. I'm being straight. I'm really breaking it to you as honestly as I can. That when you are confronted with a problem in a math class or in life, you say, well, these are my options, and I can't use that one, and I can't use that one, so apparently I'll take the log of both sides and see where it leads.
You wouldn't separate the
Right, so now look, what can we do? We have rules. We have properties. What property can we use? We have log of 5 to the x times 2 to the 2x, so we can use the product rule. So let's try. We're going to split that up over addition, so now I have log of 5 to the x plus log of 2 to the 2x equals log of 10. By the way, what's log of 10? Just 1, because 10 to the power of what is 10? 1. Well, that was nice. Now what rule can we use? Always going back to our properties, what rule can we use? The power rule. We've got some exponents up there, and those exponents can drop down in front as coefficients. So now I have x log 5 plus 2x log 2 equals 1. And at this point, do we have any more exponentials? No? Log 5 is just a number. Log 2 is just a number. This is just algebra now. This is just algebra with some painful-looking coefficients. But it's still just algebra. So I would write this down as, to put the coefficients where they should be, log 5x plus 2 log 2x equals 1. Because remember, log 5 is just a decimal, log 2 is just a decimal. Okay, we've learned a technique here. What do we do? I mean, if this was just, 5x plus 2x, we just say 7x. But how do we add these expressions now? What do we do with the x? You have to factor the x out front, so that it's log 5 plus 2 log 2. We've seen that technique now a few times, that when you're trying to add variable expressions with log coefficients, you can't really add them, so instead you factor the x out, and that way that whole thing becomes the coefficient. So now we have x being multiplied by this equals 1, therefore, to solve for x is being multiplied by this, so you divide by this. And that gives us our answer for x. X equals 1 over log 5 plus 2 log 2. So you type that into your calculator and have your answer. This is the billionth time that my phone has not gone off. I really need to check my phone and why it doesn't give me an alert. Okay, I have 1 minute. Okay, so hold on a second. let's just see where we are. Everybody take number 10. Well, no, I'm not going to cross it off. No, we do have some more E problems. Okay, when we come back, we're going to try some E problems. And then we're into log equations. These will be really fast. Some log equations, and then applications. Oh, great, folks. We're doing wonderfully. This is awesome.
Is the homework only due on Monday too?
Yeah, so let me look. Our homework will only be due, because we didn't finish 6.3. So yeah, just 6.1 and 6.2 are due by Monday. So 6.1 and 6.2, and when we come back next week, we'll finish 3, 4, and 5 all on, well, Monday and Wednesday, essentially. And here's the deal. I'll email you the practice test later today. I'll email you the practice test later today. And I'll email the solutions maybe tomorrow.